Good day, students. Welcome to mathgoserve.com. And this clip, we're going to be going over problems 6 to 10 of the Florida Algebra 1 EOC computer-based exams. If you have any questions during this presentation, feel free to ask your question in the comment section below, and we'll be more than glad to provide you with support. All right, let's take a look at question number 6. It reads, Carr is using successive approximations to estimate a positive solution to f of x equals g of x, where f of x is equal to x squared plus 13 and g of x equals 3x plus 14. The table shows the results for different input values of x. Question, use Carr's process to find the positive solution to the nearest tenth of f of x equals g of x. Okay, so what we want to do first is carry out a comparison between our output functions f and g. Okay, so what you notice is for 0, 1, 2, 3, f is smaller or less than g. Okay, so here f is less than g, 14 and 17, f is less than g, 17 and 20, f is still less than g, 22, 23, f is still less than g, but take a look at this. At x equals 4, f becomes bigger than g. And also at 3.5, f is still greater than g, although by a smaller amount, okay? So what do we know about when f is equal to g? Well, let's go ahead and write down a remark. Note, f of x is equal to g of x is between where f of x is less than g of x and f of x becomes greater than g of x. Okay, if it goes from less to greater, there's a point where they have to meet. Okay, and that intersection point is the solution. So that's the bottom line. Let me give you a visual with a number line. So let's say this is our input axis right here. So we're going from 0, let's see, how do we want to make this 1? 1, 2, 3, 4. So 1, 2, 3, 4. Okay, so these are our input values. Okay, so what's going on in this table is that from 0 all the way to 3, so from 0 to 3, what's happening? From 0 to 3, f is smaller than g. Okay, so from here to here, f is less than g. But from 3.5, somewhere here in the middle, from 3.5 to 4, so 3.5 is dead in the center here. From 3.5 to 4, it switches. And you can assume that for higher values of x, the same pattern will hold true. F becomes greater than g. So what does that tell us? It tells us that for a particular x value somewhere here between 3 and 3.5, f is going to be equal to g of x, okay? For some x. For some x in the interval 3 to 3.5. So we're going to use the method of successive approximation to determine what that x value is using this the functions and the table. All right. It's not going to be precise because we're rounding to the nearest tenth. If we wanted to do it exactly, we need to actually solve an equation. Okay. Okay, so let's go ahead and do it. So what we're going to do, let's write down what we're about to do, the remark that's guiding the whole problem solving process. Since f of 3.5 is greater than g of 3.5 and f of 3 is smaller than g of 3, the solution must be where? The solution to f of x equal to g of x, where they meet is somewhere between 3 and 3.5. Okay? All right, so we're just going with the working to the first decimal place, so the nearest tenth. So those are the input values that we are going to be using for this problem, okay? All right, so let's see, x. So we're just going to pick 3.1, 3.2, 3.3, 3.4 as our test values. So we're going to test, since we're just looking at the first decimal point, okay? Test x equals 3.1. Well, let's start from 3.4 and work our way back. Okay, 3.4, 3.4, 3.3, 3.2. We don't test 3, okay, because we already know for 3, f is less than g. Okay, all right, so what we're going to do is plug in these values into the two functions. F of x is x squared plus 13. G of x is 3x plus 14. All right, so we start with 3.4. Now, remember for the EOC, you can only use a 4-function calculator. No fancy graphing calculators on this test. So I'm just going to use a basic Microsoft calculator here. Okay. Now, first one is 3.4 squared plus 13. 3.4 square that plus 13. That's what f is, 24.56. 24.56. Let's write that down. Okay, and then let's go ahead and plug it into G. So you triple 3 times the input, 3.4, and then you add 14. And you end up with 24.2. What do you notice here? F is still greater than G. Okay, but not by too much. It's kind of shrinking, so it tells you we're kind of approaching the answer. Let's try 3.3. 3.3. So we're going to do the same process again. F of 3.3 is going to be 3.3 raised to the second power plus 13. And then we get 23.89. 23.89. And then we plug in 3.3 into the second function. 3 times 3.3 plus 14. Ooh, that's close. 23.9. But check this out. F is now less than G. So the solution is somewhere between 3.4 and 3.3. Okay? But we are asked to go to the first decimal place. So we have to pick one of these two. Which of these two is a better answer, 3.3 or 3.4? Which of them has a situation where both functions are closer to each other? If we round 23.89 to the first decimal place, guess what? It's going to be exactly equal to that. Okay? So this is our solution that we're going to pick. All right? For the first decimal place. Of course, our answer should be something a little bit bigger than that, but we want to stick to the significant places indicated in the problem. So for this problem, f of x is equal to g of x when x equals 3.3 to the what? Nearest tenth. So there goes our answer for option number 6. Okay, so for this one, let's go ahead and enter it. Remember, this is going to be a computer-based test, so just place your cursor here, click, and you enter your numerical value, 3.3, and there goes your answer for question number 6. All right, let's take a look at question 7. This is a drag and drop question. So basically you just drag answers and put it in the open spot here, okay? Question, it says Roxanne wants to test the idea that polynomials are closed under addition. Her work and explanation are shown. Drag an expression and phrases to the boxes to complete the statement. Okay, so now before we start, we have to go over one very important terminology, which is closure. What on earth does it mean for an operation to be closed? In this case, we're looking at the closure of polynomials under the operation of addition. Okay, so let's talk about closure real quick. A set of functions is closed under an operation if carrying out that operation on any element of that set results in elements from the same set. Okay, so if your polynomials are closed under addition if you add polynomials plus polynomial and get a polynomial. Okay, so let's go ahead and write that down. Polynomials are closed under addition if polynomial plus polynomial equals what? Polynomial. Okay, so that's what closure means. You don't end up with something outside. You don't end up with something outside the set. Okay, just like when well, let's just move on. Okay, so another thing assistance in answering this question has to do with what polynomials are. What do you know about the exponential term of polynomial expressions? So something to note is that exponents of the variable term of a polynomial are always integers. Okay, as soon as they become fractions, you have a radical situation. When they become negative, you have a rational function. So if you want to ensure that a function is a polynomial function, all the exponent terms must be integers. No, so positive integers must always be positive integers. Look at that part. Okay, there must always be positive integers in order for the polynomial to be the expression to be a polynomial. Okay, so let's go back to the problem. So according to Roxanne's work, he says you add this. This is clearly a polynomial expression. Now, how do we know that this is a polynomial expression? We focus our attention in this particular problem on the nature of the exponential terms. So 4, 3. What's the exponent of x? 1, right? Or how about 9, the constant? It has x to the 0 piece right there. Okay, so 4, 3, 1, 0. What do we notice about these numbers? They are positive integers. Positive integers. Of course, 0 doesn't have a sign. Okay, so positive integers right there. Okay, so that's let's take out 0. 0 doesn't really count in the context of this example. So if it's 0, it doesn't really change the whole scenario. So 4 to 1, 4, 3, 1 are positive integers. So guess what? This added right here is a polynomial. Okay, so we add this to another polynomial. So now next task is which of these three polynomial expressions, which of these three expressions is a polynomial? Okay, we have three choices. One of them is a polynomial and the other two are not. How do you figure out which is a polynomial? Focus your energy on the powers, the exponential terms. So this is 2, that's good. This is 3, that's good. Uh-oh, we have a problem here. This is negative. It's a negative integer. That's not acceptable. Okay, it has to be positive. So that automatically disqualifies this first expression from being a polynomial because one of the exponential terms is negative. It must be positive. All right, second one. Let's go to one in the middle here. Uh-oh, we have a problem. -2 is what? Is negative. You can't have negative exponential terms for a polynomial. And then if you look at this third expression here, focus on the exponents, 3, 2, don't forget about this, it's just a constant. These two numbers are what? Positive integers. So that makes this a polynomial, okay? Positive integer. So that means that this goes into our first spot. 2x to the third, 2x to the third plus 2.1x squared minus 11, okay? Now let's finish this off by basically applying the point that we noted here and use to identify the correct polynomial. The sum is closed because blank r blank, and by definition of sum, is a polynomial. So what is what? The exponents have to be what? So let's put in the first one. Sum is closed because the exponents has to be, okay, so this is good. Variables makes no sense. Coefficients, no. Integer, real, or whole numbers, which of them is correct? Remember, integers are positive numbers and their opposites. Whole numbers and their opposites. So -3, -2, -1, 0, 1, 2. Real numbers are positive numbers, their opposites in fractions and rationals. Okay, any number you can think of is a real number. But for this problem, we're restricted to only positive integers. And guess what? Whole numbers are positive integers. So for whole numbers, we have 1, 2, 3, 4, and on and on and on. These are whole numbers. It doesn't include negative numbers. So non-negative integers are whole numbers. So the correct answer is whole numbers. Okay? Remember, real numbers is integers plus rationals plus irrationals. So -3, -1/2, square root of 5, anything you can think of. So these two do not work because they include negative integers. Any number set that includes negative integers does not qualify as an exponential term for a polynomial function. That's why only whole numbers work here. Okay, so that's that for number 7. So let's go ahead and drag and drop. So this is the first one right there. So it's close because the exponents are, oh snap, integers are whole numbers. Okay, so there goes your answer. All right, let's take a look at question number 8. It says the function f of x models the value of goods that are imported into the United States, where x is the number of years since 1990. The function g of x models the value of goods that are exported from the United States. So f is imports and g of x are exports. Question: if f of x and g of x continue to model the importing and exporting of goods, then sometime in 2041, which is in 51 years after 1990, f of x is equal to g of x. Determine which function is exponential. Use a table of values to justify your choice, and then type your answer in the space that's provided. Be sure to include your function of choice. Okay, so something you want to note when comparing functions is that exponential functions always grow faster than polynomial functions, okay? So if there is a race going on, even if the polynomial function has a head start, guess what? The exponential function will eventually catch up and exceed the polynomial function. So if you look at the larger values, the larger input values, and then you see which function is taken off, that is the exponential function. Okay? All right, so let's take a look at this scenario right here. What's going on? You notice that at the start, when x is equal to 40, f is greater than g. Okay, so f has a head start, f is greater, and then at 45, f is still greater than g, right? And then at 50, f is still greater than g. And then at 51, it looks like the g is kind of catching up, but f is still greater than g, right? All of a sudden, if you take a look at 52, f becomes less than g. G has exceeded f. And guess what happens? F just keeps lagging behind, and look at the gap. G just takes off, literally. Okay? So if you look at these two functions, which one would you say is polynomial and which is exponential? Remember, exponential functions always grow faster. Even if they start behind, because of their rapid growth rates, they will eventually catch up to a polynomial function and they will leave it in the dust, so to speak. All right, so let's just write down what our answer is. So f of x is greater than g of x at x equals 40, but g of x catches up and exceeds f of x. Okay, so what does that tell us? So this means that g of x, what does g of x represent? The amount of input of wait a minute, g of x is the amount of exports, right? The amount of exports is the exponential function, because of what? Because exponential functions grow faster than what? Grow faster than polynomial functions. Okay, so all you do for this problem is as follows. You just place your cursor here and you type away. Okay, so all the remark I wrote earlier, just type it all in here, and that will be the answer to question number 8. All right, let's take a look at question number 9. It says Matthew solved the quadratic equation shown. So 4x squared minus 24x plus 7 equals 3. One of the steps that Matthew used to solve the equation is shown. Drag values into the boxes to complete the step and the solution. Okay, so we have an intermediate step and a final solution here. This is a drag and drop type question. So let's say you drag it. Let's put that back. Let's draw 3 right here. If you want to change that, just hit delete. Oh, no, you're gonna click on it. Click on that. So if you wanna delete an object, let's say assume that you accidentally drag something into the answer field. You just hit the delete, click on delete. Now delete is active, and just select what you want to delete, and then basically it takes it out. Okay. All right. So let's keep that in mind. So all we're doing here is just dragging answers and putting into these 1, 2, 3, 4, 5 boxes over here. This problem actually requires us to solve the entire quadratic, namely using the method of completing the square because I have the format here, and then we're going to drag one of the steps, input it here, and then our final answer. Okay. Okay, so let's go ahead and do it. Start with 4x squared minus 24x plus 7 equals 3. So first thing you want to do is you want to create an incomplete square, okay? And then you complete that square. So to create an incomplete square, we only need variable terms on the left side. So we subtract 7 from both sides of the equation, and we're left with 4x squared minus 24x equals 3 minus 7 is negative 4. Now we need this square isolated, so it's easy for us to complete our perfect square trinomial. So to accomplish that, we have to factor out 4 from these two terms, okay? So remember, when you factor out 4, it is as though you're dividing. When you factor out 4 from 4x squared, you're left with x squared. When you factor out 4 from negative 24x, you're left with negative 6x. Close that, equals negative 4. Okay? Now, in the parentheses, we have an incomplete square. So we want to make this a perfect square trinomial, okay? So we have x squared minus 6x, the a and b components. Now we need a c component. We have to add a number that makes this a perfect square trinomial, all right? On the right side, we have negative 4. Now, since we're dealing with an equation, anything you do to the left side, you must do the same to the right. All right, so on the left side, we're going to be adding a number here, but there's a 4 on the outside. So on the left side, guess what? We're not just adding a number, we're adding 4 times that number because of the 4 that will be distributed to the new term we are introducing. To complete a square, you have to add b over 2 squared. That's how you complete the square. Okay, add b over 2 squared, 2 completes the square. Don't forget that. Very important. Okay, now let's see, what do we have? What is b in this problem? B is negative 6. So what do we do with that? Let me change my color here. So B, this is B right here. Okay, so this A is 1, and then B is C, negative 6. So B is negative 6 divided by 2. So B over 2, which is negative 3. And what do you do next? You square it. Okay, so B over 2 squared is simply negative 3 squared. If you square negative 3, you get 9. Put a 9 here. What do we have on the left side in the parentheses? We have a perfect square trinomial. We have just completed the square. Okay, we introduced a 9 on the left side, so we have to introduce a 9 here also. 4 times that 9 since you have a 4 in front, don't forget. So that gives us 4. Now to factor this perfect square trinomial, we'll simply root the first and last terms and bring down the middle sign. Okay, don't forget that's the one you bring down. So when you square root x, we have x minus the square root of 9 is 3, quantity square. Negative 4 plus 4 times 9 is 36. Simplify again, we have 4 times quantity x minus 3 square equals negative 4 plus 36 is positive 32. Okay. So guess what? We have one of our answers. Okay, this is one of the answers we have. Let's go ahead and put that in our in the empty spots we have. So you see right here, we have 4 times x minus 3 equals what? 32. Yeah. Now we have to solve the problem, and then our final solution, we'll put it into the second row here. Okay, so to get x by itself, it's just as though we're solving an equation here. We're going to divide both sides of the equation by 4. So the goal is to get x isolated. Okay, so divide by 4, divide by 4. We're going to be using the square root property momentarily. So 4 goes here 1, 4 goes here 1. We have the quantity x minus 3 squared equals 32 over 4, which is 8. Now to undo that square, you take the square root of both sides of the equation. So we have x minus 3 equals, now anytime you take the square root of a square, you have to introduce plus or minus. Okay, plus or minus root 8. Now let's go ahead and simplify root 8. What is a simplified form of this radical? To do that, we're going to decompose it into its product of primes. So what prime number goes into 8? Since it's even, 2 goes there 4 times, and then break down 4 into 2 and 2. Now these two 2's are a square. 2 times 2 is 4. What's the square root of 4? 2. Okay, so these two 2's can come out of this 8 as 2. This stays behind because it doesn't have a partner to break out with. So you have root 8 as 2, what came out, square root of 4, root 2 that remains behind because it's not a square, as the simplified form of root 8. Okay, so let's insert that into our answer. We have x minus 3 equals plus or minus 2 root 2. To finish off, we just add 3 to both sides. And then we have x equals 3 plus or minus 2 root 2 as our answer. All right, so let's go ahead and put our answers in here. So x equals 3 plus or minus 2 root 2. So there is the answer to question number 9. All right, let's take a look at question number 10. It says the system, so the system here, p of x plus qy equals r and fx plus gy equals h has a solution 3 to negative 1, where f, g, h, p, q, and r are non-zero real numbers. Select all the systems that are also guaranteed to have the solution 3 negative 1. So this is a multiple response answer where you might have more than one correct answer to the problem. Okay? All right, so let's go ahead and do it. So one thing you will like to recall for a problem like this is the whole idea of equivalent systems. There's an algorithm that's used to solve systems of equations by addition or subtraction. The whole idea is that a system of linear equations are equivalent or has the same solution if you have one of the equations and another equation that's multiplied or divided by a non-zero constant. Okay? Or if you have one of the equation and another equation that's a constant multiple of one equation added to the other equation, or both of them are a constant multiple of one equation added to another equation, then you still have an equivalent system, a new system with the same solution as the original one. Okay, so any kind of linear combination of the two after being multiplied by a constant will generate an equivalent system. Okay, so what we're going to do is see which of these are equivalent systems. Remember, we can only multiply the entire equation by constant and add to another equation in order to generate an equivalent system. Okay, so to help us see which one is correct and which is wrong, what I'm going to do is let me rewrite my system here. P of x plus q of y equals r. And fx plus gy equals h. All right, so let's see. I'm going to call this one equation 1, and call this 2. Okay? All right, so let me show you an example of something that's legal, okay? Something of an equivalent system. So let's say this is just a side note. Example of something that works. I take equation 1 and then I double equation 2. Guess what? This is an equivalent system as that because we just have a constant multiple of the second one and the first one. Okay. Let me show you another system that's legal. Let's say I double equation 1 and then I triple equation 2 and add it to equation 1. This is legal also. Okay, you have a constant multiple of the second plus the first and double the first. This equivalent system. Okay, so these are the rules or the manipulations you can carry out to this system of equations to generate a system that has the same solution. Okay, so keep these in mind. We're going to inspect these ones one by one to see which one matches the desired format. All right, so let's look at option letter A or 1. If you look at what's going on in the first equation, you have P plus F. It looks like it's 1 plus 2, equation 1 plus equation 2, and this is clearly equation 3. Okay, so the question is this what it is? Let's test it out and see. We're going to carry out these operations on this system and see if we end up with this, if it's actually what this is, then this will be an equivalent system and it will be selected as one of the correct answers. Okay, so what's equation 1 plus 2? Equation 1 plus 2. Equation 1 plus 2 is simply what you get when you add these two equations together. So you have P, let's go ahead and write it down. You have P of X plus Q, Px plus Qy plus R, that's 1. Fx plus Gy equals H. That's equation 2. Let's go ahead and add it up. When we add it up, we're going to have Px plus Fx plus Qy plus Gy equals R plus H. All right, so let's simplify a little bit further. So there's X common here, so I can factor out the X. So I have P plus F times X plus, here I have Y common, I can factor out the Y, Q plus, what is that? Q plus G, Q plus G, Y equals R plus H. So this is what 1 plus 2 should look like. We're not sure if that's what it is, but this is what it should be. So let's look at it. P plus F times X. No, I'm looking the wrong way. So P plus F times X, that's what we have. And then the second one, Q plus G times Y equals R plus H. Exactly, that's good. And then 3 matches with 3 right here. So this is an equivalent system. Option 1 checks out. Okay. Now let's shift gears and take a look at 2. We have P plus F here. Wait a minute, this kind of sort of looks like 1 plus 2, right? 1 plus 2. And then this one over here looks strange. So let's look at the first one, 1 plus 2. We already figured out what equation 1 plus 2 is. This is it right here. P plus F times X plus Q plus G times Y. This is the legal way of doing it, right? Equals R plus H. But if you look at what we have, the first equation, you added the X's, but the Y's were not added. Is that legal? The answer is no. So it must be 1 plus 2. You cannot just add part of 1 and 2 and ignore the other part. So this is not an equivalent system since it's not a combination of both equations. It's a partial combination there. Okay, let's take a look at option 3. You have P plus QY. Oh, that's equation 1, clearly. It's equation 1 right here. And I look at this right here, 3P plus F. That looks like you tripling 1 and adding it to 2. We're not sure yet. Okay, so equation 1 and then triple 1 and add to 2. We are not sure if this is actually what's happening here. Okay, when we apply this linear combination to this system, if we don't get this exactly, then we'll just toss it out. If we get it exactly, then this is also an equivalent system. So let's go ahead and do it. So we're computing triple 1 and add it to 2. Okay, and then let's see what we get in this situation. So let's start from scratch. Px plus Qy equals R, and then Fx plus Gy equals H. So what I'm going to do first is I'm going to triple the first one, triple equation 1. Now when you triple it, you triple in every single thing, okay? That's a mistake most students make. They forget to triple the entire equation, and it results in an incorrect equation. So when I triple that, I'm going to have 3px plus 3qy equals 3r as my new equation, triple 1. And then we also have fx plus gy equals h. We're supposed to add them, right? So you're supposed to add triple 1 to equation 2. When we add it, we are going to have just to save space, I'm just going to do some work in my head. 3p plus f, both of them have x's, so let's just factor out the x's while we're at it, okay? And then in the other case here, we have 3q plus g. They both have y's, so factor out the y where we're at it, equals 3r plus h. Okay, so this is 3, 1 plus 2. The question is that what we have in the problem? Okay, so let me pull it down here. So let's see what we have. 3p plus f times x, good. 3q plus g times y, good. We have a problem. This is 3h plus r. That is incorrect. You have to triple the constant in the first equation and add it to the second equation. This is wrong. Okay, so this piece right here messes up the setup. This is not 3 times 1 plus 2, is something else. So option 3 is eliminated. Okay, now let's move on to the fourth option. Okay, so this looks like equation 1 here. And this one looks like f minus 2p. This actually looks like you're taking the second equation, f, and you're subtracting twice the first equation. We're not sure if that's what it is yet. So what we're going to do is carry out this operation. The second equation minus double the first and see if we get exactly this. If that's the case, then we know that that is an equivalent system. Okay, so what are we doing here? We're doing, let me divvy up my work so everything is within, can be seen. So we have, what are we trying to test here? Equation 2 minus double equation 1. All right, so the original system is px plus qi equals r. And then fx plus gy equals h. So what we're going to do is we're going to multiply equation 1 by -2, the entire thing. If we do that, we are going to get -2px minus 2qy equals -2r. Okay? Fx plus gy equals h. Now, when you're adding, remember addition commutes. It doesn't matter the order, okay, that you're adding. So we're just going to combine these two. To combine these two, we're going to have, so -2px plus f. If you're adding them up, so -2p plus f, they both have x's next to them. And then plus -2q plus g, they would have y's next to them. I might have a space here. This is right. And that equals -2r plus h. All right, so remember addition commute, so we can reorder our add-ins here. So this can be written as f minus 2p times x plus g minus 2q times y equals h minus 2r. So is that what we have here? F minus 2px plus g minus 2q times y equals, oh, excellent. So this is actually correct. So we have equation 1 and a linear combination of equation 2 minus equation 1. So this is an equivalent system right here. Now let's take a look at the fourth one. This one is not too bad. Option 1. The first equation is clearly equation 1. And now guess what the second equation kind of sort of looks like. 5 times equation 2. If this is the case, then this is an equivalent system. Okay, so we have the original system P. So what we're testing here is 5 times equation 2, since we already know equation 1 is correct. So px plus qy equals r. That's the first equation, and then f times x plus gy equals h. Now this setup here involves multiplying the second equation by 5. So if we multiply the second equation by 5, what do we get? Do we get exactly what we have here? So px plus qy equals r, and then 5 times f of x plus, remember, you have to distribute it to every single term. Okay, 5 times g of y equals 5h. Oh, exactly what we have here. So option A, B, C, D, E. E is also an equivalent system. So A, D, and E are correct. So let's go ahead and check the correct answers. Only the correct systems, okay? A, D, and E, or options 1, 4, and 5 for question number 10. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming for the EOC exam, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions, just ask your question in the comment section below, and we will be more than glad to provide you with support. Okay? Don't forget to subscribe to our channel for updates to the remainder of this review series. More clips can be found on math.serve.com. Thanks again for watching. And